The last thing we need to cover with light are our lenses, and we're only going to deal with converging lenses. And all a converging lens is, it's a lens that brings light rays together. They converge, they want to be together to a point, and they're thicker in the center. And this is opposite of a diverging lens where they're going to bring light rays apart. But we're only going to deal with converging. So what do they look like? They have this general shape. So they're thicker in the center, and whenever we draw lenses, this is what I'm going to use. They're thicker in the center, thinner on top, and they bring light rays together. And lenses form images. There's two types of images you can have. The first being a real image, and this is an image that forms where light actually converges. And you'll see this in ray diagrams. They'll make a lot more sense once we see this. But a real image is an image that forms where the light rays are going to meet at a certain point. A virtual image is an image that forms where light appears. So it doesn't actually converge, but appears to converge. So that would be the difference between a real image and a virtual image. Just think in terms of common sense. Virtual reality, it's not real, it just appears real. Whereas a real image, you can touch it, or not image, but something real you can actually touch, something virtual you can't, it just looks like it's there. We need a couple of definitions in order to understand what a ray diagram is going to look like, and then I'll draw a ray diagram and label all of this. The first thing is the principal axis, and that's an imaginary line passing through the center of a lens. And again, I'm going to show all of these on a ray diagram in a minute. Next, we have a focal point, and this is a place on the principal axis where light rays refract and pass through. The symbol for the focal point is a capital F, and it's just a place on the axis. The focal length is the distance between the lens and the focal point. And the symbol for focal length is a lowercase f. Next, we have image distance. This is the distance between an image and a lens. The symbol for image distance is a lowercase d with a subscript of I. And then we have the object distance, which is the distance between an object and a lens. And the symbol for this is D with a subscript of O for object. And all of this is related using the lens equation. 1 over F equals 1 over DI plus 1 over DO. So this is all reciprocals. We saw this when we were doing resistors. DO is object distance. DI is image distance. And F is the focal length. So it's a pretty easy equation to use. Given 2 of the 3, you can find the third. We'll see this, or you already saw this in the Converging Lens lab. It should have derived this equation. Okay, so let's look at what this all looks like in a ray diagram. Okay, so what would this look like on a ray diagram? That line is the principal axis. And this should be straight. I'm doing this without a ruler. Then you're going to have your lens. So the principal axis goes through the center of the lens. You have your focal point, so that would be F, that's on either side of the lens, equally distant. And then you have your focal length. I like to usually just put a dotted line through the center of the lens as a guide. You have your focal length, which goes from the center of the lens to the focal point. Then you've got your image distance and your object distance. And those distances depend on a lot of things. We'll see that when we do the cases for converging lenses. But in general, you'll have an object located somewhere. I usually show that with an arrow. So this will be the object. That was confusing with two arrows. This whole thing is the object. Don't usually circle it. And then we have our image. Usually it's upside down, but we use a dotted line and to show that's the image. A ray diagram is going to actually draw light rays to show how this is formed. So when I do those examples, you'll see this is not a complete diagram. I just wanted to point out the different definitions we just saw. So principal axis is this line. The focal point is a distance, or it's just a point on the principal axis where light's going to refract through. And this, again, will make more sense when I do the example. This right here is the lens. I use a dotted line just as a guide. Lowercase f is the distance between the center of the lens and the focal point. Your object will point upright and it'll be a solid line. Your image will be with a dotted line. It can point either up or down. We'll look at ray diagrams in a separate video. For now, we're just going to look at the lens equation. So we will come back to ray diagrams and how to draw those. It's very geometric, but we'll start with the math and then we'll get to the ray diagrams in a separate video. Okay, last thing before we really get into this, magnification. Magnification is the ratio of image height to object height. It's also the ratio of the negative image distance to the object distance. And you have the equation right in front of you. M is magnification. So this is magnification. HI, I for image, this is the image height over the object height. Negative DI would be the negative image distance over DO, which would be the object distance. So this is a three-way equation. Depending on what you're given or what you're being asked for, you'll use a combination of this. And now this brings us to the sign conventions, because signs can be confusing. Focal length is always going to be positive. Object distance is positive to the left of the lens, negative to the right of the lens. Image distance is positive for a real image and negative for a virtual image. And magnification is positive for upright and negative for inverted. And these are things that you're just going to have to memorize and know in terms of what's positive, what's negative. So let's do an example. You do have these in your packet. We'll do an example using the lens equation or the magnification equation, and then we'll add these with ray diagrams later. Okay, so you've got this in your notes. We're going to do it with just the lens equation first, and then when we do ray diagrams, we'll add in what the ray diagram looks like. So make sure you're leaving enough space at the bottom for the ray diagram. It tells us that a 2.25 centimeter tall object is 8.5 centimeters to the left of a convex lens with a focal length of 5.5 centimeters. And the image position and the height. So we are given that the object, I'm going to call that HO, is 2.25 centimeters. Its 8.5 centimeters to the left of the lens. So that's the location of the object. DO equals 8.5 centimeters. The lens has a focal length F of 5.5 centimeters. And given all that, we are looking for the image position, so that would be DI, and the image height HI. So using the lens equation, 1 over F equals 1 over DI plus 1 over DO. The only unknown here is DI. So 1 over F minus 1 over DO equals 1 over DI. 1 over 5.5 centimeters minus 1 over 8.5 centimeters equals 1 over DI. So taking the inverses of each of these, it's okay that they're in centimeters because everything's in the same unit. So as long as you're in the same unit, you don't have to worry about converting things, but just make sure that you're using all of the same unit. So the two reciprocals subtracted equal 0.0641, keeps on going, 1 over centimeters for 1 over DI. Inverse of that, DI equals 15.58, keeps on going, centimeters. We've got two sig figs, so DI is approximately 16 centimeters. And I'm taking up a lot of space. You should not be taking up this much space since you need to leave room for the ray diagram. The next thing we're looking for is the image height. We know that the magnification equals HI over HO. That should be an H, not a D. HO, which equals negative DI over DO. It's not asking for magnification, and since this is a three-way equation, we don't actually need this. We're given HO, we're given DO, we just found DI, so let's just look for HI. And this always looks like hi-ho-dee-do. That's kind of how I remember it. So rearranging HI equals negative DIHO over DO. So we're using our unrounded negative 15.5 centimeters times 8.5 centimeters over 2.25 centimeters. And this comes out to negative 4.125 centimeters. Two sig figs, HI is approximately negative 4.1 centimeters. So if you look back to our sign conventions for everything, our image height is negative because it is a virtual image. So that makes sense. So it's going to be upside down when we draw the ray diagram, and we'll look at the ray diagrams in the next video. Our object distance was positive because it's going to be located to the right of the, image distance was positive. It's going to be located to the right of the lens. Our object distance was positive. It was located to the left of the lens. So make sure you have the space because we're going to do the same exact problem with a ray diagram once we get to those. So that's how you use the lens equation. They're all pretty straightforward. You're solving for one of these 5 or 6 things. So either focal length, image distance, object distance, magnification, image height, or object height. These are really the only 2 equations that we'd be using. You might have to substitute, but other than that, it's fairly straightforward.